In the world of physics, there is a famous quote once spoken by Sir Isaac Newton that goes like this: "For every action, there is an equal and opposite reaction." While it's not applicable to everything that exists both on Earth and out in the universe, it does help sum up the general idea that there are two sides to every coin, and that not all calculations only have one answer. Of course, the possibilities of what the opposite reaction could be in regards to the universe is limitless. There is so much we already don't understand about the cosmos. It would be a fool's errand to try and attempt to figure out the opposite of the unknown. Luckily for us, while not everything in the universe has been observed, or is observable to begin with, calculations and hypothetical data have allowed us to build theories about what might exist out there and the shadows they might be casting behind themselves. What could such a pairing be? Look no further than black holes and their mysterious, unobserved counterpart, white holes. Some of the most fascinating and wondrous objects that may or may not exist in the observable universe. White holes are so similar to black holes that if you were to look at a computer-generated image of one, you probably wouldn't be able to tell the difference. White holes are theoretically possible due to the same calculations that are used to prove the existence of black holes. The debate truly starts when one considers if white holes are a separate entity throughout space-time, or if they form the opposite side of a black hole, giving literal meaning to the two sides of one coin analogy. Every white hole has the same amount of weight a black hole would have, as well as a similar rotation if the white hole is a rotating white hole. Most iconic of all, however, is the shared accretion disk that forms around white holes, just as they do around their black counterparts. The accretion disk is the layer of matter surrounding the cosmic object before the gravitational pull brings the matter in through the event horizon, the bubble surrounding the white or black hole that creates a point of no return. The only difference will come via the direction the matter moves, as white holes don't suck in what's around them, but rather spit out what's already inside of them. In other words, if someone were to observe a white hole, they would simply be viewing a black hole, but in reverse time. Space-time moves outwards in this scenario, away from the singularity, rather than towards it. When people first hear about white holes and their theoretical existence, they wonder how it would be possible for them to exist without us knowing. Surely something as powerful as a white hole emitting unlimited light and matter would create quite the spectacle in the cosmic background. The answer is the same as to why we can't see inside of a black hole. The event horizon blocks out light from actually escaping the object, just like a black hole blocks out light from entering. It becomes an even more unbelievable thought when considering white holes produce the same amount of energy through light radiation that a black hole produces through its gravitational force. What that looks like we'll only ever be able to imagine, at least with the technology we have available to us today. If you were to ask Google where in the universe white holes hide, you'll be left empty-handed. As of 2022, white holes are purely theoretical, as one has yet to be directly observed, much like black holes. The easier answer to the question, where does one find a white hole, is actually the other side of a black hole. Other calculations regard white holes to be the past version of black holes, which are just gravitational singularities seen in the future. This would make sense as to why there are no recorded instances of white holes in the observable universe. We can only see the effects of white holes, but not in practice. In the Einstein-Cartan theory, it's proposed that white holes are parent universes to smaller universes that contain even smaller black holes within them. In this scenario, a black hole with enough density and collapsing matter rebounds from within, creating the famous Einstein-Rosen bridge into another version of space-time. The black hole itself then becomes a white hole, and the density becomes infinite again. If that theory remains to be true, it would mean the observable universe that we are currently inhabiting is actually the insides of an Einstein-Rosen bridge forming within a black hole that is one of thousands upon thousands of other black holes, all creating a multiverse within a larger white hole. This would also mean the Big Bang theory was actually a big bounce scenario, in which our observable universe was born from an older, collapsed universe. Other hypotheticals refute this, claiming the Big Bang is a white hole in and of itself. This theory states that all white holes are spontaneous and matter is pushed out in a single action, forming what is called a small bang, rather than the entire collapse and creation of an entirely new universe. Despite all of the talk about white holes and their unobservable nature, it should be noted that their existence is still taken incredibly seriously by the astronomical community. They continue to be studied to this day, as the knowledge they might provide could unlock some of the biggest secrets of our observable universe and beyond. One way in which astronomers hope to learn more about white holes is their relationship with entropy and the connection it shares with the aforementioned Big Bang theory. Both the existence of the Big Bang and white holes require a breaking of the second law of thermodynamics, which states that entropy must grow as time moves forward. In order for time to be reversed, entropy would need to reach a negative value or stop completely. Of course, a dip in entropy has never occurred in the observable universe that we know of, outside of the theoretical stoppage that created our universe to begin with. However, if someday in the far, far future scientists are able to capture a moment of reduced entropy, it's possible this location would spawn a white hole, albeit very quickly. It should be noted these situations could, and probably would, end all existence as we know it, as that's probably how we were created billions upon billions of years ago. And while the physical form of the white hole wouldn't stick around for long, as its instability would only allow the object to last for a few seconds or less, what's on the other side of the white hole could contain all of the answers we've ever sought after in regards to solving time travel. Especially if the white hole was an eternal black hole in reverse. These types of white holes are infinite like their black hole counterparts, and would give us a look at real Einstein-Rosen bridges, also known as wormholes. Through these wormholes, one could find a host of possibilities, such as parallel worlds that number in the millions, as well as places that don't abide by our rules of physics and space-time at large. Infinite white holes would also swap properties, whereas time becomes space and space becomes time. This gives credence to the idea of time travel, in which we could walk along a line that represents time rather than location. Who knows what these types of discoveries could teach us? It's what makes white holes such fascinating mathematical anomalies. If you could get close enough to study one, you just might unlock all the secrets of our universe's existence. They say if you combine a white and black hole, building a time machine goes from impossible to conceivable. While committing such a destructive scenario in all of physics is unlikely to happen in this lifetime, you never know when a bridge into the next one will reveal itself and show us that there is so much more to white holes than what meets the eye. Kind of like the entirety of the cosmos itself.